It's right over there by the sink. Keep coming. Come to me. You see it behind the soap there?
Yeah.
Okay. What? That's a great pencil sharpener. It's done. That's a great pencil sharpener. It's like the best pencil sharpener I've ever had.
I'll use that the next time I'm pencil
Okay.
sharpening.
So we've got these gas particles, and they're spreading out, and they fill out the entire volume of their container. Okay? That's the first thing we need to know about gases. So they're unique in their properties. Gases are like students. There are some perfect ones, but they are very, very, very far and few between. Okay? Okay? Nobody in here, including myself, is perfect. Except for Megan. Okay? There are going to be two gases that are going to be really close to being perfect gases, and then all the rest of them are not going to be perfect. Now, in reality, there are no perfect gases. Even the ones that are close to being perfect, they're not perfect either. Okay? All right. In order to be a perfect gas, you need to obey the kinetic molecular theory. And the kinetic molecular theory says, let me just go through it and then you can write, okay? Because I'll stop the video. It says that gases contain particles, which we know, these little tiny particles, that travel in random constant straight line motion. In other words, I know. I'll leave it up there in a second. Just listen for a second, okay? These gas particles are going to travel forever and ever and ever in a straight line. Is that possible? Don't write, just listen. Can a gas particle travel forever in a straight line? If I sprayed stinky stuff up here, those gas particles are going to go whee, and they're going to start spreading out, and they're going to travel in a straight line forever. Is that possible? No. Because it's going to hit the wall, right? And eventually it's going to hit something, and it's going to bounce off, and it's going to travel in the other direction in a straight line. Okay? So if you are a perfect gas, you are going to travel forever and ever in a constant random straight line motion. There are no gases that are perfect. However, in order to use the formulas that we're going to use to practice our gas laws, we have to assume that gases are perfect. Okay? But there are no perfect gases. Now think of it this way. If you have gas like carbon dioxide gas, I'm just going to draw carbon dioxide gas for us. Okay? If you recall what carbon dioxide looks like, this is review now. You should know that it looks like this. Remember that? Okay? And in the middle you have your carbon, and on each side you have two oxygens. Kind of looks like that if I draw it in a particle diagram. This molecule is made of one carbon, two oxygens. Hydrogen is also a gas, and it looks like this. Which one's bigger? The top one, right? So the bigger the gas particle is, the less perfect it's going to be. Because when this guy hits the wall, and when this guy hits the wall, I should back up just one little second. Let's talk about you're 6 years old, 7 years old, and you go to a party and there's balloons. You ever go to a party and there's balloons? And when you get to the party and there's the balloon kind of looks like this, right? What's in that balloon? Helium. So there's helium in here. And you're like, please, 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 can I take a balloon home? Remember, you're 4, 5, 6 years old. You're like, you just want a balloon. I knew Nora wanted a balloon. Every day she's like, I want a balloon. Please let me have a balloon. And the next morning you wake up, Nora, and where's the balloon? It's not on the ceiling. It was on the ceiling when you went to bed, and the next morning you woke up and it's on the floor. Why was it on the floor? Yeah, the gas leaked out. How did the gas get out? Tiny little holes in that latex. And because this helium is really, really small, it can actually travel in a random constant straight line motion. It hits the wall of the balloon. There is a possibility that that helium is going to escape. if I filled the balloon with carbon dioxide gas, is that carbon dioxide gas going to escape as quickly as the helium?
No.
Why not? It's bigger. So the bigger your gas particles are, the less likely they are to obey the kinetic molecular theory. They're not going to be able to go in random, constant, straight line motion for as long, because the smaller the particles can actually fit through the tiny little holes and continue their straight line forever and ever. That's not a straight line, but you get the idea. It is. So if you've ever had a soda, Coke, Pepsi, Sprite, ginger ale, whatever, and it was in the basement for 2, 3, 4 years, I don't know why anyone would have it in the basement for that long, but let's just say, and you have a bottle, it's a plastic bottle, okay, and there's carbon dioxide in here, and you open it up and it's flat. Why is it flat? There's gases are escaping through this bottle. It takes years for the carbon dioxide gas to get out of the plastic bottle. It only takes 1 day, 12 to 24 hours, for the helium particles to get out of the balloon. Because the smaller you are, the easier it is for you to get through the walls of that latex or that plastic. Make sense? Okay. So, gases contain particles, and these particles want to travel for straight lines forever and ever and ever. The smaller ones can do it better than the bigger ones. That's just the way it is. Now, we want gases to be perfect, so we want the gases to be small. Hydrogen and helium gases are going to be your most perfect gases, and it's written in here somewhere. We'll get to that slide later on. Okay? Particles collide with each other and the walls of the container, we know that. And when they collide, they're going to transfer energy, and the energy is going to remain constant. So what's going to happen if you're a perfect gas? Are there any perfect gases? No. If you are a perfect gas, imagine it's 2 cars. This car is going at 60 miles an hour. This car is going at 60 miles an hour. They crash, and they bounce off each other with a perfectly elastic collision. That means this guy is going to be going back in this direction at 60 miles an hour, and the car is going to go in the other direction at 60 miles an hour. Is that possible? No. Same thing with gas particles. It's not possible. But in order for our formulas to work, we have to assume that that's what's happening. So a perfect gas, they'll hit each other, they'll bounce off, and they'll both have the same amount of energy that they started with. Perfectly elastic collisions. I do not think I wrote that on there. So I'll add it. What's the matter? Please be careful. Especially on Sunrise Highway. There's a lot of zoom, zoom, zoom all over the place. Megan graduated from the parking lot to Sunrise Highway. Good for you. Alright, the next one says, since the molecules are far apart, the volume of the individual particle is negligible. What does the word negligible mean?
Not eligible.
Nope. Negligible. SAT word. It means so small it doesn't matter. I feel like I'm at a carnival. Oh gosh. It's going from bad to worse, Olivia. That's all right. Okay? So I will put this back. Don't worry. Okay? But let's talk about what that means. So let's say you have a balloon. Oh, that is a bad balloon.
That's an awesome balloon. Nothing sleep.
You could be 6. And inside that balloon is helium. Boop, 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 boop. Okay, there's 6 heliums in there. See how tiny I made them? Okay. The volume of this balloon, okay, is the entire amount of space that balloon takes up. If I take all of these heliums that I put in the balloon and I squeeze them down, the volume of those heliums is so small compared to the volume of the balloon here that we say that the volume of these guys is negligible. It does not count. So when we're measuring the volume of a gas, we are measuring the space it's taken up, not the space that the actual molecules are occupying. That's what this means. When the since the molecules are far apart, the volume of the individual particles is zero, negligible, compared to the total volume of the gas. Okay, so we are not measuring how big the actual gas particles are. We are measuring how much space those gas particles are taking up. Okay, and then finally, gas particles do not attract one another. They want nothing to do with one another. So what are their intermolecular forces? Are they strong or are they weak? Weak. They want nothing to do with each other. That gas particle's like, see ya, and the other one's like, see ya, and we're going to go the other direction. Okay, any questions on that? All right, copy those down. I'll stop the video for a second so that we don't have to, maybe I'll stop it. Hold on. All right, back in business. There's my balloons. Okay. Just hold on. Don't write everything down. Just listen for a second, okay? Real gases are gases that do not do all those four things that we just talked about. Now, there are things we can do to make a gas behave more like an ideal gas. We can manipulate pressure and we can manipulate temperature in order to get a gas to behave more like an ideal gas. So if we go back to these for a second, okay, how can we get a gas to travel in random straight line motion more? What can we do to the temperature? Increase the temperature. So if we want a gas to do this, we need high temperatures. What?
When there's high temperatures, don't
They do. So they're going to be traveling in random straight lines for faster amount of time. They're going to just keep going. Okay? They also are going to have more energy when they collide, when they're moving faster and you have high temperatures. They are also going to be as far apart from one another as possible when you have higher temperatures. So we can get a gas to behave more like a perfect gas if we have high temperatures. How can we get a real gas to behave more like a perfect gas? We need high temperatures because the molecules are going to be moving faster. We can also get a real gas to behave more like a perfect gas if the molecules are really far apart. And we can do that by having low pressure on the actual balloon. So if I drew another balloon, okay, here's the atmospheric pressure pushing on the balloon. Okay, if I want the balloon to get bigger so the particles have more room to travel in straight lines and not hit each other, I want this atmospheric pressure pushing on the balloon to be less. So the balloon is actually going to get bigger because now I'm pushing on the outside of the balloon with less pressure, less atmospheric pressure. Does that make sense? And now these particles, let's make 4 of them in here, or 4 of them in here. These particles are probably going to hit the walls more than these guys are. They're going to travel in straight lines for longer periods of time. Capiche? Okay. So we have an acronym, and that acronym is PLIGHT. I think I have it on another page. Just hold on. Don't write anything yet. Okay? If we want real gases to behave more perfectly, we need to have low pressure, PL, ideal pressure low, that's this. Ideal gas, high temperatures. Okay, and I think I have it on another page, so hold on a second. There we go. That's what you need to write down. Write that down. Okay. There are two gases. I should switch the order of these. There are two gases that are going to be close to being perfect. They are not perfect, but they are close to being perfect. They are hydrogen and helium. And the reason why that they are close to being perfect is because they are small. They are the smallest gases we have. So they're the only two that are close to being perfect. That pretty much is everything that's on this page, just simplified. Okay? So make sure you have plight written down, which means low pressure and high temperature. And make sure you have hydrogen and helium are your closest to being perfect gases. The hydrogen and helium are going to have very weak attractive forces for one another. They're not going to attract each other. They're going to travel in straight lines for long periods of time because they're really, really small. They are going to have perfectly elastic collisions if they collide at all because they're so small, and their volume is going to be negligible compared to the volume of the container. Okay? So that pretty much sums up kinetic molecular theory. You all right, Nora? You good? You just went like this. That's how I feel on a Monday, Tuesday morning. What? Okay. Just making sure you're okay. All right. Here we go.
Oh.
Relax. It's all stuff you know already. Okay. Average kinetic energy. Just in case everybody, just so that everybody knows. One more time. What's another name for average kinetic energy? Temperature. If you see the word temperature, if you see the word average kinetic energy, change it to temperature. Everybody in here should know how to convert Celsius to Kelvin because everything we do mathematically from now until the end of the gas laws, temperature has to be in Kelvin. It cannot be in Celsius. So, on the back of your reference tables, on table T, as in taco, Taco Tuesday. Everybody loves a good taco, right, Anna? On the back of your reference tables, there is a formula for converting Celsius to Kelvin. Everything for gas laws must be done in Kelvin. And the reason for that is because Kelvin has no negatives. And absolute zero, which is 0 Kelvin, does not exist. So we will never have 0 Kelvin. Okay? And when we do the formula, which you're going to see in a second, the temperature is going to be a denominator. And you do not want a negative denominator, and you don't want 0 for your denominator. Okay? So we need to have all of our temperatures in Kelvin. All right, flip your reference tables over to table A. On the top of that first page He's either sleeping or on his phone. What is he doing? You good? Put your phone up. Well, nobody stares at their crotch. So it's either you're sleeping or you're on your phone. Okay, turn your reference tables over. You got this. On table A, you're going to see standard temperature. Standard temperature is going to be 0 degrees Celsius or 273 Kelvin. We're going to use the Kelvin for the gas loss. Okay? Doesn't mean they're not going to give it to you in Celsius. You have to be able to convert it to Kelvin. But there you have it. Standard pressure. That's the pressure we're at right now, sitting here in this room. Standard is 1 atmosphere or 101.3 kilopascals. It's given to you on table A. What they don't give you on table A is 760 millimeters of mercury and 760 torr. So on your reference tables right now, underneath where it says standard pressure, I want you to write 760 mmHg, which is millimeters of mercury, and 760 torr. Torricelli. It's the scientist's name who came up with that scale. I'm going to take a second and we're going to practice converting between atmospheres, millimeters of mercury, torr, and kilopascals. Okay. 760. It's the number's just 760. Okay? So if you are given 1 atmosphere, how many torr is that? 760. Good. If you're given a half of an atmosphere, how many torr is that? If you're given 0.46 atmospheres. Oh, now what do we do? Okay, this is how you're going to set it up. We're going to set up a proportion. We're going to say 0.46 atmospheres is to 1 atmosphere. This number being the standard, follow me here, is going to be how many torr over 760 torr. That's going to be the standard. So the bottom numbers are going to be your standards. The top number is what you're looking for and what is given to you. Match the units. Atmospheres and atmospheres, torr and torr. Write that down. Yes, you can. Because what about if you do 0.46 torr and I want kilopascals. Now what do I do? Well, what's the standard for torr? 760 torr. And what's the standard for kilopascals? 101.3 kilopascals. Yes. 760x equals 0.46 times 101.3. And then you just find x. I'm just saying, I saw it on the last Regent, so I want to make sure everybody knows how to do it. Okay? All right. Any questions on that stuff? Easy peasy so far?
No.
Will, you all right? Or no questions, or no, you're not all right? Okay. All right. Moving right along. I know, but we got a lot to do. And then the next 2 days we're going to be practicing, and then Friday you're taking the test or a quiz. All right. There are 3 main gas laws. I got good news and bad news. What do you want first? Bad news, I'm going to tell you about all 3 of these gas laws. Now the good news. They are, but flip to the back of your reference tables. You're going to see something called a combined gas law. You see it there? Okay. The combined gas law is all three of these gas laws in one formula. You do not need to know all three of these formulas. But I am going to go through them really quick with you so that you know how they operate. Okay? Gay-Lussac's law. Boyle's law, Charles' law, Gay-Lussac's law. Okay? We're going to start with Boyle's law. Okay? Boyle's law is the relationship between pressure and volume when the temperature is constant. And what do I mean by that? I mean that the temperature is not changing, but we are manipulating the pressure on the gas, not of the gas, on the gas. If I increase the pressure on the gas, what is going to happen to the volume of that gas? Here's a balloon. A lot of balloons in this unit. Okay? And I have on my balloon a pressure of 1 atmosphere. And then I take it underneath the ocean, and now my pressure on that is 2 atmospheres. What's going to happen to the size of my balloon? It's going to get smaller. So as I increase the pressure on the balloon, the volume of the gas is going to get smaller. It is an indirect relationship between pressure and volume. As I increase my pressure on the balloon, my volume is going to get smaller. You can. I would write down this thing right here. So, here, this is what you need to know. Write this down. Boyle's law. This is why I hate doing slides. Boyle's law is an indirect relationship as pressure increases, volume decreases. As pressure increases, volume decreases. That's the indirect relationship. As one goes up, the other goes down. So if I draw a chart or a graph, and I have pressure down here, and I have volume over here, as my pressure goes up, my volume is going to go down. Why do you think I made it curvy like that? Does my volume ever go to 0? No, it can't go to 0. It can get really small, but it can't go to 0. Say it again. Exponential curve. Yeah. Okay. Indirect relationship. All right, let's do the next one. Charles' law. Remember, there's going to be one formula that's going to do all of these. Okay? Charles' law is the relationship between volume and temperature. As I increase the temperature of a gas, what happens to the volume? If I start heating up a gas, it gets bigger, right? The volume gets bigger and bigger and bigger. That's assuming that pressure is not involved. No pressure. And this, my friends, is a direct relationship. As temperature goes up, ooh, what happened here? Volume is going to go up. Direct relationship. If I take a balloon outside on a hot day, the balloon is going to be slightly bigger. If I get one of those Mylar balloons at Dollar Tree and I buy it in January or February and I walk from inside Dollar Tree to outside into the parking lot, what's going to happen to the size of the balloon? It's going to shrink because the gas is getting colder. The minute you bring it back into the house, it's going to get bigger again. Okay? The volume of the gas is proportional to the temperature of that gas. The hotter the temperature, the bigger the balloon. Eventually, the balloon will pop. But as you increase the temperature, the volume is going to get bigger. Okay? That's Charles' law. And its graph looks like this. As temperature increases, volume increases. Direct relationship. All right. Last one. And again, we're going to combine all of these into one lovely formula, probably at the beginning of next period, right? Because are we getting close to the end?
1 minute.
Okay. 1 minute. Can I get Gay-Lussac's law done? Gay-Lussac's law says at constant volume. So now the volume's not changing. If I increase the pressure of a given mass of a gas, it's directly proportional to the temperature. Has anybody ever taken a can of air and pressed it down, and then what happens at the top of it? It's really cold. Because I'm decreasing the pressure, so therefore my temperature is going to decrease. Because inside that can, right, you know what I'm talking about, the cans of air? Or even a propane tank when you light your grill. If you open the top of the propane tank and let the gas come out, and then feel the top of that tank, it's going to feel cold. All right, take your break, and when we come back, I'll finish Gay-Lussac's law and